Uh, I'm going to apologize in advance to half the people here who are battery chemists and the other half who may just have general knowledge. Just for 2 minutes at the beginning, bear with me. Um, so just to set the stage, we're going to talk about batteries, obviously, but batteries in the context of the use cases that are really the evolution of energy transition, um, and uh, and a little bit of chemistry, unfortunately, is involved, but minimal. And the reason for that is that one of the things is that there is a evolution in batteries from several standpoints that is moving at hyperspeed at the moment. Uh, and a lot of the people I talk to have this very static view, like about if it has to do with their phone batteries or their cars and how they perceive electric cars, that they don't even really think of it in the context of all of the other things going on. So, so step one, I just want to do a quick concept there. Step two, we're only going to talk about the recent past, the current, and the near future. No esoteric. This might happen in 10 or 20 years. This is about what's going on now. And then inevitably, we need to talk about recycling. And that has to do with a lot of the preconceptions about the battery and the metals and the sources. That's where a little chemistry comes in, but that we can't end up with a huge pile of battery waste, nor is there a need to. And so that's kind of how it's going to go for a few minutes. And then after we get through the sort of the surface of topics, we really love to have questions. Um, and we could take the conversation in any direction that somebody wants, with the one caveat that, remember, I know there's a few people with some very deep knowledge, that the rest of the audience don't have degrees in chemistry or even know what an anode is. But so let's try to keep it not too deep. Um, the first thing that I hear is way too often is this thing like, oh yeah, like the battery of my phone goes every 2 or 3 years, and then oh, the car, well, gee whiz, maybe 5 years I have to replace my whole battery pack. And there's a truth to that, but the truth is, I'm just going to say 10 years old. 10 years old because the car you're talking about is 10 years old. And how many electric cars are there that are 10 years old? The fact is, if you buy a car today, um, take a Tesla, but it's true for most of them. Uh, there is one technical term. It's called thermal management, and the batteries that are being used today are sensitive to temperature. Very low temperatures, they can't be charged. Very high temperatures, they shouldn't be charged. They can be damaged. And so what, for instance, a Tesla or these cars will do, if you try to charge your car when it's below freezing, it has a heater in the battery. It won't let you charge it. It will first warm up the battery and then it will charge it. So you can be out in some ultra sub-zero weather. And other than the delay, it will work just fine. The second thing it will do is the same thing on the hot end, is that it will thermal manage the battery so it can't damage itself. And the important part of this is what it's led to is that if you buy an electric car today, you can expect 200,000 miles. The battery might go 25 years without having more than 20% degradation. And so that whole concept of my 10-year-old Prius needs a battery pack is not what's going to happen 10 years from now. The second thing is that conversations I have tend to be very static. We talk about lithium ion batteries and the metals that are in them and lithium mining itself. And then what about the Democratic Republic of Congo? 90% of the cobalt comes from there, and et cetera, et cetera. And so that, once again, is completely true for your 10-year-old battery. It's somewhat true today. It's becoming less true as we speak. And I'm going to let actually Florian and Hank get into that a little bit because each comes at it from a different point of view. I know Hank's already transitioned to lithium phosphate. And by the way, Tesla is too. Um, and so a lot of these preconceptions, we want to just get past them because we want to look forward and where is this going and what matters on a going forward basis. And the last thing we're going to talk about before we get into a lot of Q&A is we need to talk about the recycling, as I said. And the other misconception is, oh, I got to throw the battery away. What about the garbage? And the truth is that from a scientific standpoint, every one of those metals in a battery is recyclable. Is that the nickel and the cobalt and the manganese don't get used up. But it doesn't mean that you just throw it in a bucket and all the metals come out of the battery. And I'm gonna let Florian sort of get into the ifs, ands, or buts of that part. And so the last thing that I want to make sure people focus on is use cases. And we'll get into it, but everybody thinks of batteries in terms of their cars because of course that's what they see. And what you don't see, which is happening as we speak, and Hank's business is at one level, and then there's even a large level, which is energy storage systems that are not mobile. Um, and the thing that is very important to think about is that all those car batteries were built with ultra lightweight, high concentration of power storage. So that's of course important for a car to get range, the weight of the car. But if you think about ground storage, let's say in a mini grid or a grid storage in a small scale, the weight doesn't matter. The size almost doesn't even matter within reason. And the cost needs to be minimized and the length of life and cycles needs to be maximized. So the technology that went into creating the best car battery is in some ways um, by well, it's certainly not optimized for the use case of grid storage or local storage, and that's catching up as we speak. Um, and you can go as far as iron oxide batteries, which don't have any of the metals we're talking about. They certainly don't have the energy concentration, but in some use cases it doesn't matter at all. So that's sort of a big backdrop as to this is not your mother's battery kind of conversation. Um, and so, want to start with Florian a little bit. And actually, Florian, why don't you? We've got a bigger group here. Um, Maybe you can quickly introduce yourself and what you're doing in the space, and in a couple of minutes. And I think a lot of people know Hank, but at the risk of me not knowing who does and who doesn't, let Hank go afterwards. Go ahead, Florian.
Thanks, Andrew. Yeah, nice to meet you all. My name is Florian. I used to study chemistry. I'm an organic chemist by training, studied in Germany, Munich, and in Japan. During my PhD, realized that science is a lot of fun, but I was missing the real life application aspect of it. So I segued into a Master of Business. And ever since, I've been at the intersection of technology and business in venture capital since over 12 years. First in an institutional setting in a fund where we actually financed one of the pioneers of residential battery storage, a company called Sonnen. Then moved to a corporate setting where I built
You worked for Sonnen?
Yeah, I invested in Sonnen in 2014.
Oh my goodness.
Yes, yes. So we pioneered that space together with Christoph. And yeah, we can talk about that also later if people are interested. Yeah, moved to the corporate side, realized that it is a lot of fun with this steep learning curve, but as you progress, it becomes increasingly political, which I did not enjoy so much. So I became entrepreneurial, joined a very early stage industrial 3D printing startup as a CEO, where I helped the technical founder to turn his prototype in the garage into a product, introduce it into the market, and then we sold the business in summer 2022 to 3D Systems. And yeah, ever since the successful exit, I came back into the world of institutional venture capital, and I'm raising with my previous colleagues a 250 million euro deep tech, clean tech fund where we focus on environmental impact.
Hank,
Wow. So I'm majored in computer science and minored in Dungeons and Dragons when I went to University of Hawaii. Wrote the first role-playing game in Japan in 1983, which went on to become the #1 game in Japan in 1984. Ended up with a publishing company, started traveling around the world looking for games to bring to Japan. At the Consumer Electronics Show in 1988, I found a little game called Tetris. I went upstream. I went to the Soviet Union to get the handheld rights to Tetris. Today, I'm mostly the proud owner of Tetris. My partner is the guy who actually created the game. We've been partners since 1990 something. We are best friends forever. Tetris is still doing great. It's how can I say, the goose that lays the golden eggs. Um, I sold a company. I made a company doing mobile phone games in the US. Again, in the heyday, I was one of the first 8 companies to make mobile phone games in this country. Sold a company 3 years later for enough money so that I could buy a ranch on the Big Island. So a month after I sold my company, I had 100% blockage of the Widowmaker. On the way to the hospital, said, no, I'm not going. I still have stuff to do. Found my mission in life. My missions. First mission is to end the use of carbon-based fuel. And I started a foundation in Hawaii to do just that in Hawaii, to end the use of carbon-based fuel in Hawaii. Our claim to fame is that we were the first state in the country to have a mandate of 100% renewable energy, in Hawaii's case by 2045. 13 other states copied our legislation, so it's moving across the country. I have a new NGO in New York doing the same thing for island countries and then eventually countries, because I want to solve it from the bottom up in the world. I want everyone to stop using carbon-based fuel. Along the way, I passed a law in Hawaii that helped the solar industry. Had a boom in solar. Today, we have 37% of the rooftops in Hawaii have solar, and the electric companies stopped doing net metering. And so I thought, well, how do we get past this? Because we'd created this whole solar industry. And to find out, I decided to take my ranch on the Big Island off grid, started experimenting. My first foray with batteries were vanadium redox flow batteries, which was a horrible mistake. The name of the company was Prudent Energy, which turned out to be imprudent. And they were, after about a year, the battery stopped working and they were bought by the Chinese. We never heard from them again. I said, the next battery is going to come from a company that's still around 20 years from now, and it's going to be a chemistry I don't mind having at my ranch at the end of life. And so I found lithium ferrous phosphate, as did Sonnen in Germany. In fact, we were both using the same source. We were buying batteries from Sony. Sony is the first company to make lithium-ion batteries in 1991. And they were the first ones to have lithium ferrous phosphate, or LFP, in 2009, and then commercialize it around 2015. And then Sonnen and Blue Planet Energy, my company, started commercializing. We created products around that chemistry and that technology. Those batteries are still the best LFP batteries on the planet. They last 20 to 30 years. They're made with parts per billion instead of parts per million of purity, and they have the electronics to back it all up. So all of the systems that we've ever deployed are still working just fine. And now we are moving on to the next generation of product where we are taking on Powerwall by having a similar product that installs by one person in less than 2 hours instead of 2 people in 12 hours. So that's going to be a game changer. We've modularized everything, including the batteries, including the inverters, and including the controls. So they're all clip-on, and that makes the installation process super fast. I'm constantly looking for newer and better technologies. and I mean chemistries. As and when I find something that's better, I will switch in a heartbeat. We need longer. I think the answer to recycling is to have longer lasting batteries. So if you have a battery that lasts 30 years, you don't actually have to recycle after 15 years or 10 years or whatever it is. So
Actually, Hank, that's what Florian and I were talking about yesterday, is that, and I was telling him what's happening in the US, is that these things are gearing up, as I said at the intro, for this 10-year, 5-year-old battery, and that although we will need to recycle all these batteries, the curve of the huge demand has been and is being pushed out, just as you were talking about. I'm going to give a 2-minute intro. I don't normally, but because 361ers, most of them know me, but I see all kinds of names I've never seen before. I've one of the reasons I'm sitting here is I'm like Hank from a different era. I went to college actually to be a marine biologist, but I switched to economics and computer science at the time. There was no PC, and so to be able to do my work, I actually programmed for the university all of the statistical and econometric software and databases because we were doing it on paper. And that actually led me to my 40-year career as a professional investor. Initially in a hedge fund, because I did the same thing. I wrote trading software for myself and for my people around me. And that got me investing in technology. And this was the family office world, my first 2 decades. And the family offices wanted me to take the hedge fund, or I should say, allowed me to take the hedge fund and invest in venture capital. So I did my first VC deal in '94, and it was investing in public tech, Dell a year out of the garage, and then venture, and initially semiconductors was my signature deal when Hank was playing games. I'm joking. This revolutionized the way chips are made, and I only bring it up because it's called deep UV lithography. That's a different deep dive, but it essentially allowed Moore's law of shrinking chips geometry to the point where they're part of the chip wars you see today, and it's the core technology behind NVIDIA's chips, which we didn't talk about chips and AI, but we can one day. So, but it also, back to college for 1 second, my honors topic was,
Andy, I'm just
yeah.
worried about the timing.
Yep.
If we could,
I'm done in 10 seconds, Mark. I just
Okay.
need context. So my honors project was the global depletion of energy reserves. That's 40 years ago. And I invested in seismic technology in the 90s. So I have followed the energy train all the way to today. And I'm a technology, I'm a geek like a bunch of other people. That's it, Mark. I just needed context. Nobody needs to know my life story. Anyway, so moving on to the topics, essentially, Hank actually set the stage in a great way by saying, he moved from something he wants to have at his house, because a lot of people, that's a big thing for them, the toxicity, and we'll get to the recycling with Florian. But his comment about the willingness to move. So what I see in my inbox is all kinds of battery technologies that are this, that, and the other thing. But I basically, unless there's a prototype, I don't really want to look at. And so because essentially what we want to talk about is anything that can happen in the next 5 years and the evolution of that. Because what happens in 20 years in terms of climate,
too late.
well, it'll be too late. Thank you. Anyway, Hank, can you just continue on with that vein of that you were just talking about at the end of your intro about how you moved to LiFePO, and maybe you want to just give people 2 seconds on why that is, but why you want to have that in your house versus not wanting to have something else.
Okay, so the batteries that are in your phone or in my Tesla, That's nickel, lithium, nickel, cobalt, manganese. And that particular chemistry is the reason that you cannot put a lithium ion battery in your suitcase in an airplane, because that chemistry is volatile. It can, if you overheat it, if you puncture it, if you overcharge, if you do anything, if you shock it, it will catch on fire. And this is not fire in the traditional sense of the word fire. It doesn't need any oxygen from the atmosphere to combust. It combusts all by itself like fireworks. And so if you set a fireworks warehouse on, if you get it started, then basically the instructions to the firefighters is stand back and wait till it's over, because there is nothing you can do to stop it. Okay, so that's the problem with nickel, cobalt, manganese. Lithium ferrous phosphate, on the other end, does not have any of those problems. And so if you open up a Powerwall, which is Tesla's version of a home battery, you will find a cooling system. And I was one of the first people to have a Tesla. I have a Roadster, and it has an air conditioner in the front under the hood. And I said, can I take the air conditioner out? Because I live in Hawaii, I don't ever use it. He says, no, 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 the air conditioner, it's not for you, it's for the batteries. And so that whole concept of the battery being volatile, that's one problem. And then, of course, you've got those chemicals. You've got to reclaim those chemicals. The lithium ferrous phosphate batteries, the instructions we have from Sony at the time was landfill, because lithium and iron and phosphate are all benign chemistry. And so I like that. That was a good start. I also like the fact that they last forever. Now, what is the definition of a dead battery? The industry defines a dead battery as when it reaches 60% of its original charge capacity. And that harks back to the time of lead acid batteries, because once you reach 60%, the battery dies very quickly after that. But lithium ferrous phosphate, for example, it doesn't die after that. It continues slowly degrading. So theoretically, what you can do with a lithium ferrous phosphate battery when it's 60% is you can take it out, you can reuse it, and somebody else will gladly have a battery that starts at 60% and goes all the way down. It'll still last, I don't know, maybe decades. I have no idea. They haven't tested that far.
Yeah, no, Hank, actually, when we talk about recycling, repurposing is actually one of the subtopics in recycling. So I'm actually just going to let Florian take your line and keep going with that, and we're going to circle back to exactly what you're talking about.
Yeah, okay. So Florian, this is a good time for you to chime in.
Yeah, go, Florian.
Let me interject here. When you talk about batteries reuse, the core business here at RJ Lee is a forensics engineering laboratory. We do a lot of things like when there's fires, train wrecks, oil spills, and that stuff. We do all those investigations. We are working now with the civil engineering design groups, because there is no regulations and or specifications for buildings which are used for energy storage yet. So they're just basically building the standard building and hoping for the best. So we're working with them to design them to handle these types of problems: the heating, the cooling, the potential fire, etc.
Well, there's a whole nother side to that, and that is energy storage in buildings. So if you have an apartment building and you want to put batteries in, you do not want to have a battery that's going to do a 9/11 on your building.
You don't want to put put a bomb into it.
Yeah, so Carl, I put in the intro about micro storage, mini storage, and we're going to roll to that when we get past the battery part. So let me just go back to Florian and Carl. I'd love to have you in that, but Florian, just keep going with the batteries themselves. We have to set the stage here for the later conversation.
Sure. So, I mean, kind of what recycling options do you have? And since it's about investing and making money, what is maybe the interesting positioning? And of course, as Hank said, for certain use cases, batteries decline and then they become second life batteries, or there's companies that actually analyze the health of the battery and then try to understand, can we repurpose the cell or the pack or the whole thing? A lot of companies are looking to repurpose EV batteries for residential storage. Because if they're not good enough to charge a car at high power anymore, they still might be good enough to be used for some time in residential storage. Definitely not in a household for the reasons that Hank just described, right? EV batteries are high power density and high energy density, so essentially they're bombs. You don't want to put them into your house. As those batteries progress towards definite end of life, you will have to do chemical recycling. Basically, what you do is you have to fight against entropy and you have to separate all those metals out, which is doable. But it is something that does require a lot of capex, and it's something that requires certain scale and also requires a technology that can deal with the different cell chemistries, right? So Hank already mentioned that there's, depending on the application, there's different cell chemistries, and oftentimes the recycling technologies that are available right now, they're optimized for a certain mix of metals in the battery, so to say. So that's something that I believe as a venture capital investor is maybe not so attractive from a risk reward and also capex requirement, because you need something that is more scalable. That's why we are looking a bit more into the space of battery repurposing. Especially the analytics part is something that we find interesting, because ultimately also the residual value of the EV is determined by the health of the battery, because that's the most expensive component in the car. And in Germany, the price, I don't know how it is in the US, but in Germany, the prices for EVs are completely down. And car rental companies don't want them anymore because they cannot resell them after they've used them, because people don't understand what is the value of the car, how many kilometers is it good for. I believe there is, in the short to medium term, a lot of value to be had if you have a solution that can assess the health of the battery. Can you resell the EV at a high price? Can I repurpose the batteries in there? And what is the optimum for repurpose? And then kind of towards the end, we can go into the chemical recycling.
Okay. Why don't we actually go to that, because it ties into what actually what Carl brought up, what I brought up, which is that when your battery pack comes in and it's degraded, there's recycling, there's repurposing, as we've discussed, and so that sort of storage system that Carl's actually referring to has no problem if it's a 60% capacity, because it's not something where you run out of mileage and you're stuck in the middle of the road. So Florian, why don't you keep going and break down for us what you would recycle, what you can't recycle, and what you would repurpose.
Yeah, okay. So let's start with the repurposing and then kind of move towards the recycling part. Typically, end of life of an EV battery, and Hank, correct me if I'm wrong, but typically the definition is like 80% of the initial nameplate capacity. Typically, batteries do have a higher capacity so that the life is longer and you don't have to do full charge-discharge cycles. But anyways, so 80% of the nameplate capacity is typically considered end of life for EV. And the reason being is that it disintegrates gradually, and then after a tipping point, you get an exponential degradation, right? So if you're at 80%, kind of the next 30% is closer than the 90%, right? So it then degrades relatively quickly. If you continue to use it as a EV battery because you charge it at high powers and it's a lot of stress on the chemistry.
You're talking about nickel, cobalt, manganese.
Yeah, the high power density batteries. Of course, I understand that there is kind of cattle released last year. I believe it was what they call condensed battery chemistry. I personally haven't seen the lab data on that one, but supposedly the battery has a longer cycle life and you can stress it more because it doesn't change the volume in the charge discharge cycle so much, right? So you don't have so much physical stress in the battery anymore. And that's kind of what you also mentioned, Andrew, that the new technologies coming out will extend the life of the battery and will kind of postpone the wave of end of life
I'll
batteries.
talk about the chargers for 1 second, but I don't want to interrupt you. Keep going with your
Okay. Anyway, so then you need to analyze, can I repurpose it? And there's companies that also kind of disassemble the battery pack and then repackage the cells to match them up so that you have a good performance again. And then you can use them for stationary storage, where it doesn't really matter how much volumetric and gravimetric you have.
And just because once again, we some of us assume, I know Hank, you, but a battery pack from a car is made up of a zillion batteries. So every battery in that battery pack is not the same when it gets into that repair shop. So they're sorted by being, each cell is tested and goes into a different bin. And the repurposed bin could be half the cells in that battery, because as Florian pointed out, when you get below 80%, you get the degradation. That's the whole battery pack. That's not every battery in the battery pack. And it's important because it has to do with the whole ecosystem that has to evolve to deal with the batteries.
The battery pack is typically only as good as the worst battery in that pack.
Thank you.
Right?
Yeah.
So that's a good way to think about it.
When you have a normal battery regular one of these, like a flashlight, whatever, they always tell you don't mix different companies' batteries, and there is a reason for that. They don't like to work together if the voltages are slightly off, and that is the thing that happens over time. Now we've been talking about cells, but the newer technology where we don't have a heat problem, you no longer need to make it into a cell. The reason for cell is the space between the cells that you can use for cooling the cells to keep them from overheating and being damaged. The newer technology, they call it prismatic or pouch. It's just a different word. But in a pouch, it's sort of like a flat object with the leads coming out of the top or the side, and then you can put them all next to each other. If you don't have a heat problem, then you can just pack them in, and that gives you better energy density, and it also gives you a different a different shape for you to play with when you're building your battery module, your battery pack.
And Hank, for everybody here, you'll also see the term solid state battery, and it's what Hank's talking about as well. It's not liquid. It's all one unit.
Well, okay, so the liquid that you're referring to is the what is it called?
Electrolyte.
An electrolyte. So every battery
yeah.
has an electrolyte in it, and so yeah, the pouches are different, and we're looking at graphene pouches now. They can make any battery chemistry into a pouch, but of course you can't do NMC in that way because the ones in the middle are going to overheat, and then you're going to have a problem. But LFP, you could make that into a pouch as well. I did talk to the government, the Department of Energy, about giving me money to make a module factory. And they said, how about building a cell factory? Would you like to build a cell factory? And it's because they don't want to hand out anything less than $500 million.
They already are, by the way, yeah.
And I said, no, I don't want to build a cell factory because I'm not convinced that cells are going to survive. By the time I finish my cell factory, the form factor will have changed, and I'll have built this factory for nothing.
And I think that's a very important a topic also, right? So when we built Sonnen, basically a system integrator like you're building, Hank, we were at, it was like almost 10 years ago. We thought about, okay, do we need a proprietary battery cell technology to differentiate ourselves, or is it actually smarter to build the hardware system and the electronics in a way that we are actually independent of proprietary battery cell technologies, and instead we can integrate the latest, greatest on the market? And I believe that's still the right approach today, because it's changing fast, and especially what's coming out of Asia is just scaling much faster, and it's incredibly difficult or impossible to predict which technology is going to be the successful one. That's also why we stay away from battery cell technologies, because there's no way to have a repeatable edge in that space, in my opinion.
And I just wanted to also bring back, because it's tied into this, Florian, you mentioned something about charge speeds, and I mentioned the smart technology of thermal management. Hank's talked about obviously the need or not need in certain cases. Carl talked about, having certain standards. But there's one thing here that is another misnomer. So your Apple phone, by the way, if you hit battery preserve, it will only charge when it gets down to 20%. It will stop at 80% as a really crude way, quite frankly, of extending battery life. But your high-speed charging station, when you take your car there, what it'll do is it'll very quickly get your car to 80%, and then it'll start to go really slow to do exactly what Florian is talking about. It's managing so that it's not destroying your battery. But really, once you get used to that, when the high-speed chargers, when they work and they're ubiquitous, we're in the United States, unfortunately. I don't know when that is. But anyway, when you are at one, it will not destroy your battery, because what it will do is that it will quickly charge it to 80%. And you should just drive off at that point. Don't bother trying to fully charge your battery unless you're going into the wilderness.
Yeah.
So these smart systems, and Hank, I don't want to get too off into smart systems, but smart systems are inside battery. We didn't even talk about a BMS. Every battery pack has a battery management system that is a smart system inside. Then smart systems on the outside. Hank's application does that as well. And in fact, the whole integration, which is we're getting past it, but smart systems are everywhere. So they compensate for some of these problems. So even my dumb e-bike, Hank and I both have e-bikes. Unfortunately, they don't have thermal management, but it's not going to blow up because it's not going to let it overcharge. One of my daughters is like horrified. I keep it in the house. And so there's a lot of these misconceptions is my point. So, and, I'm actually, at this point, let's see if there's any questions out from the audience, because I was trying to get past the misinformation part. But if anybody wants, based on what we had, just, if you can raise your hand is helpful, but, instead of everybody talking at once. Anybody out there?
Yes,
Sanjeev has. Andy, take a look at the chat too.
I wasn't. I apologize.
Go ahead, Sanjeev.
So yeah, I have a couple of questions. One about supercapacitors. That what are the applications there? And the second one is in general, not only related to supercapacitors. What is the effect of how quickly you can charge a battery of any type, different chemistries, of course, and cycle count, like how many cycles it can maintain, and what does it take to move the needle on that front? Like what are the physics aspects or chemistry aspects that are preventing a battery from being charged instantaneously, for example?
Sanjeev, can I just tell everybody what a supercapacitor is first, or do you want to? Okay, so anyway, a capacitor is not a battery. Basically, they've been around forever. They're in computers and things. They store up electricity very, very quickly. And unlike a battery, they can release electricity very, very quickly. So that's, like I said, they're not new. But what Sanji's referring to is the evolution where supercapacitors, for the reasons I discussed, are ways of essentially storing energy. I say like a battery because they don't work like a battery. And he's asking where they can be substituted. Hank or Florian, do you want to, or I can if you don't.
I'll go, and then Hank, you
go,
just,
Florian, go ahead.
Yeah, so capacitor has a high power density, right? So it can discharge a lot of energy in a very short period of time, but it cannot do so for a long period of time, right? So if you want to drive a car on supercapacitors, that's not really possible. So there's a fundamental difference in what supercapacitors are used for. So you can put a lot of power into it, but you can only do so for a very short period of time.
So they have evolved to not be that instantaneous. And what I've seen, Sanjay, I don't know, you can, if you see different, I've seen them used in combination with
Yeah.
energy storage systems
That's right.
because one of the constructs of the batteries we are talking about is their ability to deliver a lot of power very quickly is limited. They cannot just discharge the whole battery at a infinite rate. And
Right,
so
different duty cycles.
yeah, well, not just the duty cycle. There's a certain amount of total storage of a battery. The amount of amperage as a percentage can only be discharged on a real-time basis at a much, much lower level. So the capacitor can act in between on the input and output of that battery to, and this doesn't apply to a car, by the way, to other uses where more instantaneous power for a short period of time is needed. So I've seen them used in combination. They are evolving. People have talked about them replacing a battery, as Florian described. We're very far away from that happening.
Yeah, so the NMC has the advantage of being able to discharge pretty quickly, relatively quickly, which is what gives my Tesla ludicrous mode. But if you look at my house, if my house is in ludicrous mode, I'm having a serious problem somewhere. So I really don't need ludicrous mode in my house. It will never need that kind of a surge, if you will. So I'm much more interested in a battery that doesn't get hot. So the reason that you can't charge a battery, this is what I think, I don't know if this is true, Florian, you correct me if I'm wrong, is the battery will overheat because there's heat during the charging. And if you've got an NMC, then that heat will eventually cause internal combustion, or what is it, spontaneous combustion. With the LFP battery, that's not so much an issue. And so when we connected our batteries in the first place, when we started getting into the battery business, the inverters or the charge controllers coming from the PV on the roof going to our batteries, they were babying the batteries. And that's because lead acid batteries don't like to be charged too quickly, and same thing with NMC batteries. But LFP don't have that problem, so we had to reprogram the firmware on the inverters so that they would charge quicker. Now, we just talked about supercapacitor, and I'm in the business. I'm confused. I hear that there are supercapacitor / graphene batteries. Some people call them graphene batteries. They're definitely not all graphene. They have some graphene in them. But they use the word supercapacitors. So they basically charge and discharge 4 times faster already than the LFP batteries or the NMC batteries. So I don't know what the repercussions of this is as far as EV batteries is concerned going forward. But I do think that this is a kind of a revolution that we're in, where the line between a capacitor and a battery is kind of becoming unclear. And that's a useful transition.
The energy storage, sorry, go ahead.
No, sorry, Sanjeev.
Yeah, so the energy storage ability of a capacitor is related to the area of the 2 plates, and inversely related to the distance between them.
Yes.
So the best you can do is to have a 1 layer thin atom, which is graphene, can be a perfect insulator, coated by 1 layer of gold, 1 layer of gold, and then so you can take a football field's worth of area and fit it into the palm of your hand. And it has a tremendous amount of capacity to store energy. But you're right, all of you guys are right. It has a very high discharge and low, like high charge and high discharge time, meaning it's not going to discharge slowly over time. You need extra electronics on the output side of things. But I was just curious to see if that's
the question is where do you need capacitors, right? So I don't think there's that many applications where you really need it. One that I've seen is kind of where you want to recuperate the energy from braking, because there you do release a lot of energy in a short period of time, which is too much power to recharge a battery. And then I've seen some ideas where people kind of buffer it in a capacitor and then transfer it to a battery.
Well, Florian, I go back to just, I said, smart chargers also do thermal management. They won't overheat your battery. They'll measure the temperature and they'll throttle the amount of power going in, depending on that. So that is a problem we've solved already. So anyway, anybody else, off of anything else, related to this? Michael.
Yeah, I'm going to be pasting something into the chat box to, be able to limit what I'm having to say verbally. But next month, we're going to be breaking ground on building 2 new battery, starting with 1 battery factory in Wisconsin. And then we're going to be later replicating that in Nigeria. And we're also developing 2 new battery technologies. One is zinc air. Somebody mentioned earlier the iron air or iron rust batteries.
Iron oxide, iron air. Yes.
Iron oxide flow batteries. And so we're going to be doing a zinc air one as well as a hemp carbon one. And we're developing both of these in conjunction with the University of Wisconsin and Milwaukee. They have a major development center there, and Dr. Chu is the head of that one that we're working with.
As soon as you have something that works, let me know. We take your batteries and build them into modules. And if they're competitive in the market, we'll switch in a heartbeat.
Is that Dr. Gordon Chu?
Diang Chu, and it's QU is the spelling of the last name. Yeah.
Sorry. Thank you.
No problem.
Andy, did we talk about solid state batteries? I put a link. Prolosium just announced a huge plan.
Yeah, I brought it up because it was a parallel to what Hank's talking about of not necessarily needing space. Toyota keeps saying they're coming out with this amazing new solid state, and it's in the software world, Hank, we called it vaporware. People talked about all these things, and there never was. So who knows?
But to be fair, there's a Taiwan plant revving up. There's a 5.5 billion plant going up in France, and in several 361ers are investors in it. So I'm just curious if your thoughts on it.
So I've looked at it, and so far I've only seen working prototypes. And so it's definitely been a proven technology in the lab. And from a manufacturing production standpoint, so far nobody has produced a solid state plant that has a visual product.
Look at the link. I don't know, Florian or Hank, if you've heard of this company. Prolosium.
No, I have not.
I mean, I could describe what a solid state battery is, but
please.
Go for it.
So just so people know what the heck we're even talking about, is essentially the liquid electrolytes are eliminated from the solid state battery and replaced with elements that don't flow. Just like I said, I don't want to talk chemistry. You have an anode, a diode. The electrolyte allows electrons to flow from one to the other. That's charge discharge. Okay, that's the whole thing we're talking about here. So the solid state battery doesn't have a liquid electrolyte, so it can't explode. For instance, it can't be punctured and then damaged in the same way. And that's why people want them for cars. And as I said, I mean, I'll look at this and put it in the 361 chat later today, but we don't want to do it. So, Charles, what's on your mind? Charles Manto.
Thank you. Just a quick idea for comment. You know how hospitals all have a third to half of their power supplied with backup generators in case the grid goes down for any period of time. What's interesting as a concept is for every community and every element like a hospital, a local unit of government, a National Guard base, a school, to be able to make half of their own power from what's over their head, under their feet, or right next door, and then be able to store it efficiently so that every element of society could become capable of making half of the power that they need right on site without anything from far away, making it possible for them to operate in island mode and then take or basically de-risk our society from having to be at risk of a grid failure on one hand. And the other, if we call that local energy, 95% of the time, that local energy source of overhead, underfoot, or right next door will become renewable. And by
Yeah, so Charles,
yes.
so Charles, just the point is I'm gonna send it to Hank in 1 second because what you're talking about are microgrids, and we did do one on utilities. We touched on microgrids, and another deep dive will be talking about integrating. The reason we're talking about batteries today, and I said in the intro, I said we're not just talking about cars, and we're talking about batteries now being used for ground storage, mini storage, grids, large scale grid storage. By the way, there's an army base in Colorado that has pump storage. There's hospitals doing this. So unfortunately, we can't get too broad. But because Hank is laser focused on this, I'm just going to give it to him for a quick answer to that.
Yeah, just after Hurricane Maria in Puerto Rico, they had 120 emergency shelters that all failed because they had no power after the hurricane. The lines went down. So the Red Cross decided to fix that problem and funded 120 schools, that's the emergency shelters, schools, to have PV and batteries. And my company did all of the batteries for the 120 schools in Puerto Rico. And more recently, there was an earthquake in Puerto Rico. Again, everybody went to the emergency shelters. This time, they all worked because they all were able to island. They all had their own PV, they had their own storage. Now, if you're talking about a building like a hospital, I think the issue gets the taller the building, the relative to the amount of energy that building needs, you have less roof space. So if you've got a one-story building or a two-story building, you probably have enough roof space to power the entire building. But if you're talking about a 10-story building, now you don't have enough roof space anymore, and you have to go to the surrounding area to get your extra energy.
Hank, I actually built I'm sorry to cut you off. I'm gonna go to Florian because we're almost out of time. But I built, by the way, a mini model of a Walmart that if you covered all the cars in the parking lot with solar, did it actually equalize the building? I actually built a model of it. So yes, all of that but it needs to be worked out in each instance. And I just gave you an example. Florian, the last thing, because we have to cover this before we stop. Talk about recycling. So when all these batteries come in, okay, what happens? What do we have? What do we not have? What have we solved? What are we left with?
Yeah. So basically, we have or what happens today is you take a battery that's end of life and then it's shredded. So you make a mix of everything. And then you try to extract through a chemical process. You try to extract all the metals out of it again so that you can reuse them. And that is not an easy process. It's also not very safe, depending on how you've pre-treated the batteries. Could cause problems. So not everybody is set up to do it. And as I mentioned earlier, it's kind of CapEx intense. And what's probably going to happen going forward is as people try to embed circularity as a concept in product design, is probably there is a good way forward to actually design the batteries without having to reinvent the cell chemistry, design the batteries in a way that you can much easier separate the different materials without having to shred it. Because in the end, what you're doing is you're fighting against entropy. And if you kind of can avoid increasing more entropy through the shredding process, it's much easier and cheaper to recycle it. I don't know how which way we want to go, but
no. So just give us, the big picture. When that happens, as you just pointed out, I want to emphasize that battery manufacturers should be designing their batteries to be recycled, and they're not. We'll just leave it at that because somebody else can push that topic, but it's not happening, and it should happen because it's totally doable. But Florian, what are we left with in terms of metals that we can reuse, garbage that we have to dispose of, and anything in between?
Yeah, it depends on the cell chemistry. That's kind of the scientific answer. But basically, you can recover the
Broad.
metals. I would say almost completely. If you have an organic electrolyte, that's something that you have to deal with, and you need to kind of remove it. That's going to waste mainly. Looking at the value chain, so there's companies that do the shredding and then they extract what's called black mass. This is kind of the gold where all the valuable metals are inside, and then there's recycling companies that take the black mass and extract the metals out of it.
And what's
Here-
left that we can't use? What's left that we have to dispose of? What's left?
There is some kind of slack that we need to dispose of, and you never can recycle 100% because it's just
Of
not.
course, but and what's in that slack? What is that slack? What's in there?
That's a good question. Probably a mix of the input factors.
Okay.
Well, here's my issue with the recycling is, you know, in a couple of years, we're going to figure out that we no longer need cobalt or manganese for our batteries.
Yeah.
Then where is the how can I say, where are
Or
the people that
lithium.
are going to, or lithium, you know, where are the companies that are going to need those minerals at that point in time? And right now we need them. We can recycle them into more batteries. But if we all switch to carbon batteries or whatever in the future, then those will be, I don't know, back to being whatever they used to be.
Well, they're actually expensive and rare, so there are uses for them, and we'll simply stop mining lithium, cobalt, manganese, and we'll never have to mine it ever again.
Well,
I
nice.
don't think
That
that's
would be-
that's not going to happen because we're just not going to recycle those batteries because there is no value in them, and then you have created a lot of
No, I'm
waste.
saying we use cobalt for other things.
Of course,
That's
of course, of course. But what
Yeah.
kind of Hank's argument is kind of this is kind of our traditional use of cobalt, and then kind of on top is the battery usage of it. And once we have developed a chemistry where we don't
Yeah.
use cobalt anymore, nobody's going to recycle the cobalt out of the cobalt batteries or the batteries as a whole
Right.
because
So the
it's
manganese
not.
is already out. The
Yeah.
cobalt is next. And by the way, I didn't want to get this, but do you know that silicon is in the lithium anodes because it greatly improves the anode, and it's only in the lab, which is why I don't talk about it. A silicon anode can charge 10 times as fast and hold 10 times the power as a pure lithium anode. So that transition will, as Hank brought up, we use less and less lithium. We're already gotten rid of manganese, I believe. Less and less cobalt. Nickel is a common element, but once again, it's used for all kinds of things anyway.
So
So